resonances which are observable in the light coming out from the structure, we have a situation where we can get an assessment of the different antigens and the relative amounts of the antigens present in the fluid sample taken from the bottom. Next one. Very rapidly, we want to use polymeric materials. That was the choice for this technology. We can have refractive indices as high as about 1.8 as the maximum, and at low, we're targeting as low as refractive index of water. It's not a coincidence that we're targeting 1.33 with this polymer, even though it may be quite difficult to find the right polymer. We're making, therefore, an index-free kind of waveguide structure. This is a cross-sectional view. High refractive index core, lower refractive index cladding. That top layer may itself actually be removed in order to let fluid, which is water, get close to the surface of the waveguide core. So why are we talking about water? We're talking about water because the standard way that one delivers the biological material is to dilute it and then transport it with water. So we're dealing, water is a naturally available material. It can be, of course, very pure material until we put something into it. And so we're dealing with something which is a refractive index close to 1.33, if not exactly the same. This is the same device structure here, but now we're looking at plan view. The plan view shows us with a stripe waveguide, a so-called bus waveguide, distributing light along. And if it's close enough to this adjacent stripe of waveguide, it can couple light into that waveguide. And we can make a cavity by having a periodic structure. So this is Bragg reflection. So it's a periodic mirror structure made by changing the dimensions laterally on a nano scale. Two mirrors, one here and one here, with a spacer section in between them, can make a high quality factor resonator. Typically resonance quality factors of tens of thousands are the area that we're talking about. Next one. So again we come back to nano-imprint lithography. The technique which is presently being implemented, and not without difficulty, is again to take our stamp or mold, again it's formed in silicon, to press it into the polymer. So this is the high refractive index polymer, PI stands for polyimide in this case, on top of a lower refractive index polymer, commercial material known as Cytop. So we have the cladding layer here, the core layer here, which we're deforming to form the stripes, and we can form both stripes and we can form corrugations which make us a Bragg mirror, a periodically varying reflector structure. And we can go depths as deep as 1 micrometer, which is what is the requirement in this case. So this is an application of nano-imprint lithography where, in fact, the polymer that we're deforming is the polymer from which we are making our device. It is the polymer in which we're going to propagate light. Light in the infrared at a wavelength about 1.3 micrometers. Yes. Right, now I change to split ring resonator structures. So these are the atomic units of a metamaterial. They're one atomic unit of a metamaterial. So I joke a little bit about the word meta. I actually did a little bit of literary research on the word meta. It comes from the Greek language and it's used both to mean structures above and beyond, and also, of course, related to the word metal. And it's by essentially semantic coincidence that our metamaterials are typically made up of arrays of metallic structures. So it's a coincidence the word meta, or that part comes in. So this is a pattern made in metal. It's a fairly thin pattern in metal. These are just characteristic dimensions. We're showing the electric field vector of the light that's going to interact with that structure, pointing out we tend to have two different basic orientations with respect to this U-shaped metal. And for electrical engineers, for those who think they understand something about electrical engineering, the point to make is that the fundamental resonance of this structure can be classified as relating to capacitance and inductance. It is an LC resonance, a classic electrical resonance. The classic electrical resonance, for those that are sufficiently largely physicists, which I take to be quite a large number of those present, the LC resonance is, if we do it in the right way, a manifestation of the so-called Fano resonance. So when Fano identified certain behaviour to do with resonance, he was really merely identifying something which electrical engineers had already identified as their LC resonance. It's basically the same thing. There are issues in there. Although we can say capacitance, inductance, and in the classical electrical circumstance it will be a lumped capacitance and a lumped inductance, in this case it is distributed, but we can still talk about an equivalent capacitance and an equivalent inductance. And I'm stressing all that because there are also resonances which are obviously plasmonic resonances. And those that want to talk about propagation of waves coupled electron photon oscillations propagating in this structure with a velocity which is characteristic of light propagation, but slow light propagation. We have a boundary condition here and a boundary condition here. If we bring these close enough together, in a sense they share the boundary condition. But we can get a resonance which can be the fundamental resonance, which is what these are identifying in the reflection versus wavelength spectrum of an array of these structures. This resonance here is to do with propagation between here and here and a boundary condition where there will be a maximum or a minimum depending on the electric field component. So this will be approximately half a wavelength at the plasmon propagation velocity in this structure. And that's the fundamental plasmonic resonance, but it's not the fundamental resonance of the structure. So for those people that insist on talking about plasmonic resonances, you better admit that the LC resonance is a zero-order plasmon resonance, if you want to call it by a particular label, and still label it as plasmonic. There are higher order resonances. We can talk about me resonances, but we have to take very careful account of the shape, because if we bring these two ends close together, we can modify the knee resonance so much that it actually starts to look again like an LC resonance. Its orientation depends on the electric field. So if the electric field is across the surface, across this gap, we get the LC peak in the reflection versus wavelength spectrum, and we also get at shorter wavelengths, higher frequencies, a plasmonic resonance, which is characteristically sharper. If we orient the electric field vector of the light so that it is along the fingers, we do not see the LC resonance. It is exactly at a null for excitation of the resonance, and we see a resonance peak only, which is the plasmonic resonance. We can couple that. Next one. Right, now I'm switching to a modified version of the structure, and I'm showing a micrograph, an array of these structures on a scale of 4 micrometers. So these are resonators which have 2 splits in them, so they're multiply split. There's an asymmetry, which is why we call it the asymmetric split ring resonator, where this branch of what is a complete circle with a gap in it, this branch is longer than the branch on the right-hand side. And this is a schematic of one element. So these are, we're looking at arrays of elements. These are periodically distributed elements, and it is common when people talk about metamaterials to say they are periodic arrays of elements, and those elements have the basic property which determines the behavior. The important point is, actually they do not need to be periodic. It is not intrinsic to metamaterial behavior that you have a periodic distribution. It is that you have something which can have some version of resonant behavior. So it's the resonance of these individual elements that determines the behaviour. If they are far enough apart, the coupling between them is unimportant. We still get the metamaterial property characterised by the individual elements. If we push them close enough together, there will start to be interactions between the elements, and then you will get effects which will depend on whether the arrangement is periodic or some other distribution, which may be completely random in principle. So it's a second order effect, if you like, how the things are distributed is the fundamental property coming from the individual elements, which is of interest. That's just another image of a particular structure fabricated in the, so this is one element. This was published a little while ago. If we take an array of these elements and we deposit an organic material, which indeed could be a biologically derived organic material, and I'm using the word organic slightly more strictly in the chemistry sense, that is compounds made of carbon. And the compound made of carbon that we put onto the surface is polymethyl methacrylate. So we are depositing a thin layer of PMMA, and we take these resonances in the reflection. It's a very characteristic resonance behaviour. There's a reflection peak, and a strong dip in the reflection, which we can identify as a kind of trap mode. It's a high absorption mode of these structures. I should also add that when I talk about the resonances of these sections in here, I definitely am talking plasmonic. This structure, because of the two gaps, the LC resonance, not so much it doesn't exist, it's just that we don't see it because it's shifted to a sufficiently high frequency that it's not within our interest spectrum. So I put down polymethyl methacrylate, PMMA on top. I get this curve here, the red curve. I get a reflection peak which is shifted simply because I've changed the refractive index above the material, above the structure. I've changed the refractive index, so I shift the resonance. So I shift this reflection peak, I shift this reflection peak across, I shift the dip across. That feature in there is a spectral feature just of the atmosphere. It is at a wavelength above 4 micrometers, so it's probably the presence of CO2 in the atmosphere, which is important. But what I've also got on here is what I like to call a super-Fano resonance. It's a super-Fano resonance, which is going up and down characteristically like a Fano resonance does, but it's going up and down several times, which depends on the thickness of the PMMA. So I'm getting a very strongly enhanced interaction near this reflection peak, and it will look quite different if I shift the structure, if I shift the resonance of this structure with respect to the molecular resonance. So this feature here is due to the resonance of one particular component of the molecule of polymethyl methacrylate. It is the carbonyl bond resonance. There are other features in here which come from other parts of the molecular spectrum. This is characteristic of the particular compound that we're looking at. So what we have is the opportunity to make resonantly reflective structures which hit resonances related to specific properties, we hope known properties we're looking for of the molecules of organic material that we have deposited on the surface. The layer thickness of the molecular organic layer is of the order of 30 nanometers in this case. So we published something more recently on the resonance hybridization in these structures. Really, it's an intellectual exercise which it took us a long time to work through. Next one, please. So we can get a reflection peak associated primarily with this part of the structure. We can get at a different wavelength. Because it's shorter, we get a resonance at a smaller wavelength from this one. These are arrays of this element, then we have arrays of this element, and then we take arrays of the combined structure, and we can see resonance for the left-hand arc